Hello there, and welcome to Sleepy Science Vault. In the late summer of 1977, two small spacecraft left Earth within just weeks of each other, carrying with them the quiet ambition of an entire species. Their names were Voyager 1 and Voyager 2, and their story would become one of the most remarkable journeys ever attempted by human hands. To understand why they were built, we have to look at the sky itself, and at a kind of cosmic coincidence that comes along only rarely. Once every 176 years, the outer planets of our solar system fall into a specific alignment. Jupiter, Saturn, Uranus, and Neptune drift into positions that allow a single spacecraft to visit all four using something called a gravity assist, a technique where a spacecraft borrows a small amount of momentum from a planet's own gravitational pull, using it like a slingshot to fling itself toward the next distant world without needing enormous amounts of fuel. This kind of alignment last occurred in the late 1970s. And it would not happen again until the 22nd century. Scientists at NASA understood what an extraordinary opportunity this was. A window like this comes along only once in a human lifetime, sometimes not even that. If they could design spacecraft capable of surviving the journey, capable of enduring years, perhaps decades, in the frozen silence of deep space, they could accomplish something that would otherwise take generations of separate missions to achieve. So the mission was born. At first, it did not carry the name we know today. In its earliest stages, the project was called Mariner Jupiter-Saturn, a fairly plain, technical name for what would eventually become one of the most poetic journeys in the history of exploration. It was only later that the name changed to something that better matched the spirit of what these spacecraft were meant to do. Voyager. A traveler. A wanderer through worlds. The original goal was more modest than what the mission eventually became. The plan was simply to study Jupiter and Saturn, the two largest planets in our solar system, two immense worlds of swirling gas, powerful storms, and mysterious moons. But the rare alignment of the outer planets offered something more. If the trajectory was right, if the timing was precise, a spacecraft could continue on, using Saturn's gravity to bend its path onward to Uranus, and then to Neptune. A grand tour of the outer solar system, made possible by a celestial coincidence that would not return for nearly 2 centuries. It was an opportunity too remarkable to let pass by. And so, 2 spacecraft were built, not 1, but 2. So that if anything went wrong with the first, the second could carry the mission forward. Twins, in a sense, each carrying nearly identical instruments, each designed to endure the same impossible distances. In August of 1977, at Cape Canaveral, Florida, the first of the 2 was made ready. It might surprise you to learn that the spacecraft that launched first was not Voyager 1, but Voyager 2. On August 20th, 1977, Voyager 2 lifted off atop a Titan Centaur rocket, rising slowly into the humid Florida sky, carrying with it years of engineering, hope, and the accumulated knowledge of thousands of people who had worked to make this moment possible. Then, just over 2 weeks later, on September 5, 1977, Voyager 1 followed, launching from the very same site, on a similar rocket, beginning its own journey into the dark. It seems almost backwards, doesn't it? Voyager 1 launching after Voyager 2. But the reason is simple, and rather elegant once you understand it. Voyager 1 was placed on a faster, more direct trajectory. Even though it launched later, it was designed to overtake its twin and reach Jupiter first, and eventually to travel farther and faster than any human-made object ever had before. Voyager 2, meanwhile, was set on a longer, more careful path, one that would allow it to visit not just Jupiter and Saturn, but continue onward to Uranus and Neptune as well, worlds that Voyager 1 would never see. So although Voyager 2 left the ground first, it is Voyager 1 that we usually speak of first, because of how far, and how fast, it would ultimately go. 2 spacecraft. 2 paths. 1 shared purpose. As these machines climbed away from Earth, they carried more than scientific instruments. They carried something deeply, quietly human. Attached to each spacecraft was a golden record, a phonograph disc made of gold-plated copper, sealed and protected, meant to endure for hundreds of millions of years in the vacuum of space. On it were recorded sounds and images meant to represent life on Earth, the sound of wind, of thunder, of laughter, of a mother's kiss, of birdsong, of human languages spoken in greeting. Music from different cultures and centuries. Photographs of mountains, oceans, cities, and faces. It was, in the truest sense, a message in a bottle. Cast into the vast, dark ocean of space, with no certainty that it would ever be found, and no way of knowing who, or what, might find it. Each record included spoken greetings, simple, warm words offered in dozens of languages, extended toward any form of intelligent life that might someday intercept these small, drifting machines. A kind of hello, sent outward without expectation of reply, a hopeful gesture from a young species reaching quietly into the dark, wondering if anyone, or anything, might one day be listening. There is something profoundly moving about that. 2 machines, built of metal and circuitry, sent out not just to measure and observe, but to greet, to represent us, to carry a piece of who we are, long after the hands that built them have returned to dust. As Voyager 1 and Voyager 2 climbed higher above Florida in those late summer days of 1977, they were leaving behind more than just the launch pad. They were beginning a journey that would carry them past every planet humans had ever dreamed of visiting, and eventually, beyond the very edge of our solar system itself. But that is a story for what comes next. For now, let them rise. Let them fall silent against the stars. 2 golden records turning gently in the dark, carrying Earth's quiet hello into the endless unknown. The choice of what to place on that golden record was not left to chance. It was carefully, thoughtfully assembled by a committee, led by the astronomer and writer Carl Sagan, a man who understood, perhaps better than most, how to speak about science with wonder rather than cold precision. Sagan and his team spent months deciding what would best represent humanity to an audience they could never meet. What sounds mattered? What images captured something true about life on Earth? It was an almost impossible task, trying to summarize an entire species, an entire world, onto a single small disk of gold. But they did it, with care and with heart, and the result became one of the most quietly beautiful artifacts humanity has ever created. While that record carried Earth outward, the spacecraft themselves were carrying something back. Between them, Voyager 1 and Voyager 2 would go on to study 48 moons scattered across the outer solar system, along with the rings and magnetic fields of the giant planets they passed. Worlds that had only ever appeared as faint points of light through telescopes were about to become real places, with landscapes, weather, and mysteries of their own. The first of these giant worlds to be reached was Jupiter. On March 5, 1979, Voyager 1 made its closest approach, passing by at a distance of roughly 277,400 kilometers. To us, that number might sound vast, but in the scale of the solar system, it was remarkably close enough to reveal details no human eye had ever seen. 4 months later, Voyager 2 followed, making its own closest approach on July 9, 1979, though at a slightly greater distance of about 650,180 kilometers. Together, the two spacecraft gave scientists something they had never had before, not just a glimpse of Jupiter, but a genuine, detailed portrait of it. And what they found there changed the way we understood the solar system entirely. Among Jupiter's many moons, one in particular captured the world's attention, a small, strange, colorful moon called Io. From a distance, Io had always seemed like just another rocky satellite, one of dozens circling the giant planet. But as Voyager 1 drew closer, its cameras began to reveal something extraordinary. Io's surface was covered in odd patches of yellow, orange, and red, and scattered across it were shapes that looked, unmistakably, like eruptions. Volcanoes. It seems almost hard to imagine now, but before this moment, no one had ever seen an active volcano anywhere beyond Earth. Not on Mars. Not on the Moon. Nowhere. Our own planet was, as far as anyone knew, the only place in the solar system with that kind of restless, fiery geology. Then Voyager's images showed towering plumes rising from Io's surface, enormous eruptions, some reaching hundreds of kilometers into space, far taller and more powerful than anything Earth's own volcanoes produce. It was a discovery no one had fully anticipated. Io, this small moon orbiting a much larger, more famous planet, turned out to be one of the most volcanically active places ever observed, anywhere. Think, for a moment, about what that meant. A tiny world, dwarfed by Jupiter's overwhelming presence, was nonetheless alive with its own violent, beautiful geology, constantly reshaping itself, venting sulfur and heat into the black vacuum of space. It was a quiet reminder that even in the coldest, most distant reaches of our solar system, there can be fire. The cause, scientists would later understand, came from Io's relationship with Jupiter itself. The immense gravitational pull of the giant planet, combined with the gravity of its neighboring moons, stretches and flexes Io internally, a kind of continuous, invisible squeezing. That flexing generates heat deep inside the moon, heat with nowhere to go but out, erupting again and again onto the surface. It was, in its own way, a beautiful piece of celestial mechanics, gravity itself, quietly setting a distant moon on fire. For the scientists watching those images arrive back on Earth, it must have felt like witnessing something almost impossible. Here was proof, undeniable and vivid, that geological activity, the same kind of restless energy that shapes our own planet, was not unique to Earth after all. It existed elsewhere too, in places far colder, far darker, far stranger than anything we had imagined. And it was only the beginning. Jupiter itself, the giant world these two moons orbited, revealed its own secrets as the Voyagers passed. Its swirling clouds, its centuries-old storms, its faint and previously unknown rings, all of it came into focus for the first time, transformed from distant blurs into a living, breathing world. But it was Io, this small volcanic moon, that perhaps left the deepest impression. A reminder that wonder often hides in the places we least expect it, not always in the largest, most obvious worlds, but sometimes in the small, overlooked ones, quietly burning at the edge of everything we thought we knew. As Voyager 1 and Voyager 2 continued on their long journey outward, they carried these discoveries with them, encoded in data, transmitted patiently back across hundreds of millions of kilometers of empty space, arriving on Earth as faint signals, pieced together into images that would change textbooks, inspire new questions, and remind an entire generation just how much remained undiscovered. Jupiter was only the first stop. Ahead lay Saturn, with its impossibly delicate rings, and beyond that, worlds even Voyager's engineers had once considered almost mythical in their distance. But for now, let the image of Io remain. A small moon, glowing faintly against the darkness, its volcanoes rising silently into space, a quiet, fiery signal that even in the farthest corners of the solar system, something is always moving, always alive, always becoming. Even after Io's volcanoes had stunned the scientists watching from Earth, Jupiter was not finished revealing itself. The discovery of active volcanism on that small, restless moon remains one of the defining moments of the entire mission, the first confirmation that Earth was not alone in its geological restlessness, that fire and motion existed elsewhere in the solar system too. It set the tone for everything that followed. If a modest moon like Io could hold such a surprise, what else might be waiting in the shadows of this giant planet and its many companions? As it turned out, quite a lot. As Voyager 1 continued past Jupiter, its instruments picked up something unexpected, flickering in the planet's dense, swirling atmosphere. Lightning. Not the kind we associate with distant thunderstorms here on Earth, but something happening on an entirely different world, deep within clouds of ammonia and hydrogen, far from any ocean or coastline. It was the first time lightning had ever been detected on a planet other than our own, a strange and oddly familiar sight, appearing in a place so utterly alien. Somewhere in that vast, churning atmosphere, storms very much like our own were quietly discharging their energy, illuminating clouds no human eye would ever directly see. There is something comforting, in a way, about that discovery, the idea that even on a planet as immense and foreign as Jupiter, some of the same physical forces that shape our quiet evenings on Earth, the gathering of clouds, the buildup of charge, the sudden release of light, were also present, playing out silently, millions of kilometers away. But Jupiter held more surprises still. As Voyager 1 drew closer, its cameras detected something incredibly faint, almost invisible against the blinding brightness of the planet itself, a thin, delicate ring, encircling Jupiter's equator. It was nothing like the grand, dramatic rings we associate with Saturn. This ring was subtle, faint, composed of fine dust rather than ice, easily overlooked, easily missed. And yet, there it was, proof that Jupiter, too, wore a ring of its own, quiet and unassuming, drifting silently around the planet. Alongside this discovery came two small, previously unknown moons, later named Phoebe and Métis, tiny worlds, barely more than fragments compared to the giant planet they orbited, yet significant all the same. Each new moon discovered was a reminder of just how much remained hidden, waiting patiently in the darkness for a spacecraft to finally arrive and notice it. Voyager 2, following months behind its twin, added still more to this growing list. As it moved past Jupiter, it identified yet another moon, the 14th to be confirmed around the giant planet, one more small companion, added quietly to Jupiter's already crowded family. In this pattern, spacecraft passing distant giants and uncovering worlds no one had known existed, would only continue as the mission carried on. Over the following years, as Voyager 2 pressed onward past planet after planet, it would go on to discover 3 new moons at Jupiter, 4 more at Saturn, an astonishing 11 at Uranus, and 6 additional moons at Neptune. Each of these small, previously invisible worlds had been drifting in the darkness all along, silent and unseen, waiting for a set of cameras built by human hands to finally catch a glimpse of them. It's worth pausing on that for a moment. Before Voyager, our entire understanding of the outer solar system rested on faint points of light and careful mathematical guesses. Astronomers could calculate that certain moons must exist, based on subtle gravitational influences, but they could not see them, not clearly, not in any real detail. Voyager changed that completely. It transformed distant, theoretical worlds into places with shape, texture, and identity. It turned mathematics into geography. And it wasn't only new moons that Voyager 2 uncovered. As it passed by each of the giant planets in turn, it also became the very first spacecraft to capture images of the rings surrounding Jupiter, Uranus, and Neptune. Until that moment, only Saturn had been widely known for its rings, its grand, glittering halo, visible even through modest telescopes from Earth. But Voyager 2 revealed that ring systems were not unique to Saturn at all. They were, in fact, a common feature of giant planets throughout our solar system, faint, delicate structures of dust, ice, and rock, some barely visible, others more defined, each one quietly encircling its planet like a fragile, ancient bracelet. It reshaped how scientists thought about planetary formation altogether. Rings, it seemed, were not some rare cosmic accident. They were simply what happened, under the right conditions, around massive worlds with enough gravity to gather and hold onto scattered debris. But perhaps one of the most quietly profound discoveries during this stage of the journey came not from a ring, or a storm, or even a volcano, but from careful, patient observation of another one of Jupiter's moons. Europa. At first glance, Europa appeared almost featureless, a smooth, icy world, pale and simple compared to the fiery drama unfolding on nearby Io. But as Voyager's cameras captured closer images, something curious began to emerge. Long, winding cracks stretched across its surface, some straight, some gently curved, forming intricate patterns across the ice like fine lines etched into glass. Mixed among them were darker streaks, areas where something other than pure ice seemed to be present, staining the surface in subtle shades of red and brown. Scientists studying these images began to wonder, what could cause such patterns? On Earth, similar cracking often occurs when ice shifts and moves over something fluid underneath. Could the same be true here, on this cold, distant moon, orbiting a planet more than 700 million kilometers from the Sun? It was only a hint, a faint suggestion, nothing more. But it was enough to plant an idea that would grow steadily more important in the decades that followed. Perhaps, beneath Europa's icy shell, there was liquid water, a hidden ocean, sealed away from the vacuum of space by miles of solid ice, kept warm not by sunlight, but by the same kind of gravitational flexing that had set Io's volcanoes ablaze. At the time, it was only a whisper of a possibility. But that whisper would go on to shape decades of scientific curiosity, inspiring future missions, fueling endless questions about where else in our solar system life might quietly exist, hidden beneath frozen surfaces, far from the warmth of any sun. All of this, the volcanoes, the lightning, the rings, the newly discovered moons, the mysterious cracks across Europa's icy face, emerged from a single, extended encounter with one giant planet and its sprawling family of worlds. Jupiter alone offered more discoveries than anyone had dared to expect, transforming a distant point of light into an entire, complex system worthy of years of study. And yet, this was still only the beginning of the journey. Ahead, Saturn waited, with its rings, its storms, and mysteries entirely its own. Voyager 1 and Voyager 2 were only getting started. But for now, let Jupiter fade quietly into the distance behind them. Let its lightning flicker one last time in the dark. Let Europa's frozen cracks catch the faint light of a sun that, from here, looks impossibly small and far away, a quiet reminder of just how much remains hidden, waiting patiently in the cold, silent places we have only just begun to explore. Before we leave Europa behind entirely, it's worth returning to that small, icy moon once more, because what Voyager found there deserves a closer look. This was not just an interesting curiosity glimpsed in passing. It was, in many ways, the very first strong evidence that an ocean might exist somewhere beyond Earth. Think about what that idea actually means. For as long as humans had looked up at the night sky, Earth had always seemed singular in one very specific way. It was the water world. The blue planet, defined by its oceans, its rivers, its rain. Other worlds were dry, or frozen, or scorched, or shrouded in gas. Water, in its liquid form, seemed to belong to us alone. And then Voyager's cameras drifted past Europa, and captured something quietly extraordinary. Across the moon's pale, icy surface, long cracks stretched in winding, deliberate patterns, and within many of those cracks was something unexpected. Not empty gaps, not simple fractures, but dark material, filling the lines like ink settling into the grooves of old, weathered stone. The color and texture suggested something other than plain ice, something that had, perhaps, welled up from beneath the surface, seeping into the cracks before slowly freezing in place. Scientists studying these images began to ask a quiet but powerful question. What if this moon was not simply solid ice all the way through? What if, beneath that frozen shell, something was moving, shifting slowly, fracturing the surface from below, allowing darker material to rise up and seep into the widening gaps? It was, at the time, only a hint. Nothing could be proven outright from these images alone. But it was enough. Enough to suggest, for the first time with real scientific weight, that liquid water might exist somewhere else in our solar system, hidden not on the surface, where sunlight could never reach it, but deep beneath miles of ice, kept warm by forces we were only beginning to understand. It's a strange thing, to feel a sense of wonder over a scatter of dark cracks on a distant moon. But that's precisely what happened. Scientists on Earth, sifting through Voyager's transmitted images, found themselves looking at something that quietly reshaped how we thought about the possibility of life beyond our own planet. If water could exist there, even hidden, even frozen over, then perhaps Europa was not simply a dead, icy world after all. Perhaps it was something far more interesting. A place worth returning to. A place worth studying more closely, for decades to come. And so it was. Later missions would eventually follow this earliest of clues. But it all began here, with a handful of grainy images and a scientific team willing to ask, what if? With Jupiter's secrets slowly being cataloged and sent home across the dark distances of space, the two spacecraft continued onward, deeper into the solar system, toward a planet that many considered, even then, to be the most beautiful in our cosmic neighborhood. Saturn. On November 12, 1980, Voyager 1 made its closest approach, sweeping past the ring giant and gathering an extraordinary wealth of detailed information about both the planet itself and its remarkable collection of moons. For years, Saturn had been admired from a distance, a soft, golden sphere encircled by rings so wide, so distinct, that even modest telescopes on Earth could make them out clearly. But admiration from a distance is one thing. Arriving up close, gathering real data, capturing real images, that was something else entirely. As Voyager 1 approached, Saturn slowly transformed from a distant, painterly image into something vast and almost overwhelming. Layers of pale clouds banding across its surface, subtle storms swirling within its atmosphere, and of course, those rings, growing larger and more intricate with every passing hour, resolving from a single, simple band into countless individual ringlets, each one distinct, each one shaped by forces scientists were only beginning to fully understand. But among all of Saturn's many moons, more than 60 are known today, one stood out above all the rest, drawing particular attention from the mission's scientists. Titan. From Earth, Titan had always appeared as little more than a hazy, oranged, tucked quietly among Saturn's larger family of moons. But as Voyager 1 drew closer, it became clear that Titan was unlike almost anything else in the solar system. Unlike most moons, which are typically airless, rocky, or icy worlds with essentially no meaningful atmosphere, Titan was different. It was wrapped in a thick, hazy shroud of gas, an atmosphere far denser than anyone had expected to find on a moon. As Voyager's instruments studied this atmosphere more closely, the results were remarkable. Titan's atmosphere, it turned out, was composed primarily of nitrogen, the very same gas that makes up the vast majority of Earth's own atmosphere. In fact, in terms of surface pressure, Titan's atmosphere proved to be roughly 1.6 times as thick as Earth's own, a strange and unexpected similarity, considering how utterly different the two worlds otherwise were. Titan orbits far from the Sun, bathed in a cold, dim light, its surface temperature far below anything survivable by human standards. And yet, wrapped around this frozen moon was an atmosphere that, in its basic composition, felt eerily familiar, almost as though some faint echo of Earth had been placed, quietly and inexplicably, in the outer reaches of the solar system. It's worth sitting with that thought for a moment. Here was a moon, smaller than our own planet, orbiting not the Sun directly but a much larger planet, itself far from the Sun's warmth, and yet, it had managed to hold on to a thick, nitrogen-rich atmosphere, thicker even than our own. Nowhere else among the countless moons and planets Voyager had encountered so far had anything quite like this been found. Titan was not simply another icy, airless rock drifting through the darkness. It was something more complex, more mysterious, a world wrapped in its own private atmosphere, hiding its surface completely from view beneath a thick orange haze that Voyager's cameras simply could not penetrate. What lay beneath that haze, no one could say for certain, not yet. The thick atmosphere blocked any clear view of Titan's actual surface, leaving scientists with tantalizing questions rather than concrete answers. Was the surface rocky? Icy? Could there be lakes, or rivers, hidden beneath that orange veil, filled not with water, perhaps, but with something else entirely, some exotic liquid capable of remaining fluid in such deep, persistent cold? These were questions Voyager alone could not answer. But simply by identifying Titan's dense, nitrogen-rich atmosphere, the mission had already accomplished something remarkable. It had revealed that this small, distant moon deserved far more attention than anyone had previously imagined. It planted a seed of curiosity that would, many years later, inspire an entirely separate mission, one designed specifically to descend through that thick orange haze and finally reveal what lay hidden beneath. But all of that still lay far in the future. For now, in November of 1980, Voyager 1 continued its careful study of Saturn and its many moons, gathering as much data as it possibly could before continuing its long, solitary journey outward. Titan's atmosphere remained a mystery, glowing faintly orange against the blackness of space, its secrets patiently waiting for another day, another mission, another set of curious human eyes. Saturn itself continued to reveal new details with every passing hour, intricate patterns within its rings, subtle variations in cloud color, faint storms rotating slowly across its vast atmosphere. Each new image sent back to Earth added another small piece to a growing portrait of this enormous, elegant planet, a portrait that, until Voyager's arrival, had existed only as a distant, idealized image, admired but never truly understood. It's remarkable, really, to consider how much changed in such a short span of time. Only a few years earlier, Saturn had been little more than a beautiful shape in the night sky, its rings a source of quiet fascination for anyone who happened to look through a telescope. Now, thanks to Voyager, it was becoming something far richer, a complex, dynamic system, home to moons like Titan, each one carrying its own quiet mysteries, waiting patiently to be uncovered. As Voyager 1 continued past Saturn, preparing to leave the ringed planet behind, its instruments still gathering final measurements, its cameras still capturing final images, there was a quiet sense that this moment marked another turning point in the mission. Jupiter had shown us fire in the volcanoes of Io. It had shown us the tantalizing possibility of hidden water, locked away beneath Europa's icy shell. Now Saturn, too, was offering its own quiet revelations, rings more intricate than anyone had imagined, and a moon wrapped in an atmosphere strangely, hauntingly similar to our own. Two golden records, still carried faithfully aboard each spacecraft, continued their slow, silent journey outward, passing now beyond Saturn's rings, carrying with them not only messages from Earth, but an ever-growing collection of new discoveries, findings that would, in time, filter back into classrooms, textbooks, and the quiet imaginations of anyone who ever looked up at the night sky and wondered what might be out there. Ahead, still, lay Uranus and Neptune, distant, icy worlds that no spacecraft had ever visited before, waiting patiently at the far edges of the solar system. But for now, let Saturn's rings catch the pale, distant sunlight one final time. Let Titan's orange haze drift quietly at the edge of vision, its secrets still safely hidden, still patiently waiting. And let Voyager 1 continue on, steady and unhurried, carrying its collection of new discoveries outward into the dark, toward whatever quiet wonders still lay ahead. Even as Titan's hazy secrets drifted quietly out of reach, Saturn had more to offer. The planet's family of moons, it turned out, was larger than anyone had confirmed before Voyager 1 arrived. As the spacecraft moved through the Saturnian system, its instruments picked out 5 new moons, small and previously unseen, each one adding to the growing sense that these distant, ringed worlds were far more crowded, far more complex, than telescopes on Earth had ever revealed. Faint, icy bodies, some barely more than a few kilometers across, had been orbiting Saturn all along, hidden simply by distance and by the limits of what human eyes, even aided by the best instruments of the time, could actually see. Alongside these newly discovered moons came another quiet surprise. Voyager 1's cameras revealed yet another ring encircling Saturn, one that had not been part of the planet's well-known ring system as astronomers understood it before the mission. Saturn's rings, long admired as a single, elegant structure, were proving to be something far more intricate, layer upon layer, ring within ring, some bright and broad, others thin and faint, merely lost in the glare of the planet itself. Each pass, each new image, added further detail to what was quickly becoming one of the most complex and beautiful structures ever studied in the solar system. It's worth pausing here, just for a moment, to consider how much had already changed. Before Voyager, 5 new moons and an additional ring might have sounded like modest, almost minor discoveries. But taken together with everything found at Jupiter, the volcanoes, the lightning, the hints of a hidden ocean, it was becoming clear that the outer solar system held far more detail, far more nuance, than anyone had previously imagined. Nothing out here was simple. Nothing was quite as expected. As Voyager 1 completed its work at Saturn, something quietly significant took place, a decision, made carefully by mission planners, that would shape the rest of its journey in a very particular way. In order to get a close, detailed look at Titan and its mysterious atmosphere, Voyager 1's trajectory was bent upward, angling its path above the plane in which the planets orbit the Sun. It was a deliberate trade-off. By choosing this route, Voyager 1 would gain extraordinary insight into Titan, but in doing so, it would also leave the plane of the planets entirely, ending any possibility of visiting Uranus or Neptune afterward. Its path would carry it upward and outward, away from the solar system's central disk, toward the vast emptiness beyond. Voyager 2, meanwhile, followed a different course. Rather than angling upward, it continued along a path that dipped below that same orbital plane, a route carefully chosen to preserve its opportunity to visit not only Saturn, but Uranus and Neptune as well. Two spacecraft, launched within weeks of each other, now diverging in a very real, very physical sense, one rising above the solar system's disk, the other dipping quietly beneath it, each following its own long, solitary arc into the outer dark. It's a striking image, if you take a moment to picture it. Two small machines, having traveled together in spirit if not in exact company, now parting ways above and below the very disk of planets they had once shared. Voyager 1, having completed its primary planetary mission at Saturn, would continue climbing outward, eventually becoming the most distant human-made object in existence. Voyager 2, meanwhile, still had planets ahead of it, two worlds that no spacecraft, before or since, has ever visited: Uranus and Neptune. Even today, Voyager 2 remains the only spacecraft ever to have flown past either of these two distant, icy giants. Every image, every measurement, every scrap of close-up data we have about Uranus and Neptune, all of it traces back to this single spacecraft, and this single, extraordinary journey. No other mission has ever ventured that far to study these particular worlds directly. In many ways, Voyager 2's encounters with Uranus and Neptune remain unmatched, even decades later, a quiet testament to just how rare and how remarkable this mission truly was. It also means that Voyager 2 holds a distinction unlike any other spacecraft in history. It became the first, and so far the only, spacecraft to fly by all four of the outer giant planets: Jupiter, Saturn, Uranus, and Neptune, completing what scientists had once only dreamed of achieving through that rare planetary alignment back in the 1970s. What began as an ambitious plan to take advantage of a once-in-a-lifetime opportunity had, by the time Voyager 2 approached Neptune, become an accomplished reality, a genuine grand tour of the outer solar system, carried out by a single, patient spacecraft, sending its findings home across ever-increasing distances. To this day, no other mission has matched that achievement. Voyager 2 remains the only spacecraft to have studied all four giant planets up close, a record that has stood for decades, and may well stand for decades more. It's a quiet kind of legacy, not loud, not dramatic, simply true. A small, aging spacecraft, launched in 1977, remains, even now, utterly unique in the history of space exploration. But before reaching Neptune, there was still Uranus to encounter, a planet unlike any other in the solar system, tilted strangely on its side, spinning almost sideways as it orbits the Sun. In January of 1986, Voyager 2 arrived. For the very first time, humanity received close-up, detailed images of this pale, distant world, a planet that, until that moment, had existed largely as a faint blue-green disk, barely more than a smudge even through the most powerful telescopes available. Suddenly, thanks to Voyager 2's cameras, Uranus became something real. Its subtle, hazy atmosphere came into focus, its faint rings became visible in far greater detail than ever before, and its collection of moons, previously known only vaguely, began to reveal individual character and identity. Uranus, in many ways, presented a quieter, more understated kind of beauty compared to the dramatic swirling storms of Jupiter, or the vivid, expansive rings of Saturn. Its atmosphere appeared calm, almost eerily smooth, its pale blue-green color coming from methane gas high in its atmosphere, absorbing red light and reflecting back that soft, distinctive hue. It was strange, and strangely peaceful, to look at images of a planet so different from anything encountered so far in the mission, a world spinning almost on its side, tilted at an angle unlike any other planet in the solar system. Scientists studying these first close-up images found themselves faced with an entirely new set of questions. Why was Uranus tilted so dramatically compared to every other planet? What forces, long ago, might have knocked it onto its side, leaving it to spin through space in such an unusual orientation? Voyager 2 could not answer every question it raised, but simply by finally providing real, detailed data about this distant, mysterious world, it transformed Uranus from a faint point of curiosity into a genuine subject of ongoing scientific study. It's easy, perhaps, to overlook Uranus in the story of Voyager's journey, quieter, less dramatic than the fiery volcanoes of Io or the impossibly intricate rings of Saturn. But in its own understated way, this encounter represented something remarkable. Humanity, for the first time, was looking closely at one of the most distant and least understood planets in our entire solar system, a pale, tilted world, drifting slowly through the outer dark, finally revealed in detail after centuries of being little more than a faint smudge in the eyepiece of a telescope. And Voyager 2 was not finished yet. Beyond Uranus, one final planet remained, the most distant of all the giants, waiting quietly at the very edge of what we then considered the boundary of our solar system. Neptune. But that encounter, that final planetary chapter, still lay a few years ahead, drifting somewhere in Voyager 2's future, patiently waiting as the spacecraft continued its long, solitary journey outward. For now, let Uranus turn slowly in the pale sunlight, its rings faint and delicate, its atmosphere calm and unreadable. Let Voyager 2 continue on, steady and quiet, carrying its collection of discoveries ever deeper into the solar system's outer reaches, toward one last giant world, waiting somewhere in the cold, patient dark ahead. As Voyager 2 drew closer to Uranus, its cameras did not stop at the planet's pale, hazy atmosphere. They turned their attention, too, to something far more delicate and easily overlooked, the faint rings encircling this strange, tilted world. Until this moment, Uranus's rings had been known only in the barest sense, detected years earlier through a clever, indirect method, watching how the planet's light dimmed briefly as it passed in front of a distant star. Astronomers had inferred the presence of rings without ever actually seeing them directly. They were, in essence, a kind of shadow of a discovery, something known to exist, but never truly observed. Voyager 2 changed that completely. For the very first time, the spacecraft transmitted close-up images of Uranus's rings, revealing them not as some vague theoretical structure, but as real, physical features, narrow, dark, and strikingly different from the wide, bright rings that circle Saturn. Where Saturn's rings shimmer with ice and reflect sunlight in broad, luminous bands, Uranus's rings prove to be thin, dim, almost secretive, composed of much darker material, absorbing more light than they reflected. It gave them an entirely different character, quiet and understated, much like the planet they surrounded. There is something fitting about that, in a way. Uranus itself had always been a quieter, more mysterious presence among the giant planets, tilted strangely on its side, wrapped in a smooth, pale atmosphere that gave few obvious clues about what lay beneath. Its rings, too, seemed to share that same reserved, understated nature, narrow threads of dark material, easily missed, easily overlooked, yet no less real, no less significant, than the grander rings found elsewhere in the solar system. With Uranus now studied in detail, Voyager 2 continued on, carrying its instruments, its cameras, and its two golden records ever further outward, toward one final planetary encounter, the last of the giant worlds still waiting to be explored. Neptune. By the time Voyager 2 approached this distant, ice-blue planet in the summer of 1989, it had already been traveling for 12 years. 12 years of launches, flybys, discoveries, and quiet, patient adjustments to its trajectory, each one carefully calculated by scientists and engineers back on Earth, guiding this small spacecraft across distances that are almost impossible to truly comprehend. And now, finally, it was approaching the very edge of what was then considered the outer boundary of the solar system's major planets. No spacecraft had ever traveled this far before. No human-made object had ever come close enough to Neptune to study it directly. Until this moment, everything we knew about this remote, icy giant came from faint observations made through telescopes here on Earth, a small, dim, bluish, barely more than a pinprick of light against the vast darkness of space. In 1989, that changed. Voyager 2 became the first, and to this day the only, spacecraft ever to fly past Neptune, completing an achievement that, decades earlier, had existed only as a hopeful possibility, dependent on a rare planetary alignment and the successful survival of a spacecraft across 12 long years of deep space travel. It also meant that Voyager 2 held a truly unique distinction in the history of exploration, the first, and still the only, spacecraft ever to visit both Uranus and Neptune. Two icy giants, tucked away at the far edges of our solar system, visited by a single, remarkably resilient machine that had, against considerable odds, managed to keep functioning across more than a decade of continuous operation in the cold vacuum of space. As Voyager 2 approached Neptune, its cameras began capturing something unexpected, not the calm, muted atmosphere many had anticipated, but something far more dynamic and alive. Neptune, it turned out, was not simply a quiet, distant world drifting silently at the edge of the solar system. It was, in fact, remarkably active, its atmosphere swirling with visible weather patterns, deep blue clouds streaked with wisps of white, and, most striking of all, an enormous, dark storm system, later named the Great Dark Spot, churning steadily within its upper atmosphere. For scientists watching these images arrive back on Earth, it was a genuine surprise. Neptune orbits so far from the Sun that it receives only a tiny fraction of the sunlight and warmth that reaches Earth. By most expectations, such a cold, distant world should have been relatively calm, its atmosphere sluggish and largely inactive. Instead, Voyager 2 revealed some of the fastest winds ever recorded anywhere in the solar system, tearing across Neptune's atmosphere at speeds that, even now, remain difficult to fully explain. Here was a planet that received almost no warmth from its distant sun, and yet somehow generated weather patterns more violent, more dynamic, than almost anywhere else Voyager had visited. It was, in its own quiet way, one of the mission's most unexpected discoveries, a reminder that distance from the Sun does not necessarily mean stillness, or silence, or calm. Even in the coldest, dimmest reaches of the solar system, powerful, restless forces could still be at work, driving storms and winds across worlds that had, until now, existed only as faint, still images through the lens of a telescope. But Neptune itself, remarkable as it was not the only discovery waiting in this final planetary encounter. Orbiting this distant, ice-blue giant was a moon unlike almost any other in the solar system, a moon that would, in its own way, prove just as astonishing as Neptune's storms. Its name was Triton. On August 25, 1989, Voyager 2 captured the very first close-up images ever taken of this strange, distant moon. Until that moment, Triton had remained almost entirely a mystery, a faint point of light orbiting Neptune, its surface, its composition, its true nature, completely unknown. Scientists had little more than educated guesses to work with. But as Voyager 2's cameras turned toward Triton, something remarkable slowly came into view. Triton, it turned out, was unlike any other moon Voyager had encountered throughout its long journey. Its surface appeared pale, icy, and strangely smooth in places, marked here and there by unusual, cracked terrain that resembled, in some strange way, the skin of a cantaloupe, a pattern scientists had never seen anywhere else in the solar system. But it was not simply Triton's unusual surface texture that captured everyone's attention. As Voyager 2's instruments continued observing this distant, icy moon, they detected something almost unbelievable. Triton, despite existing in one of the coldest environments in the entire solar system, temperatures there hover far below anything survivable, among the lowest ever recorded on any body Voyager had studied, was not entirely still. Dark streaks stretched across portions of its icy surface, extending for kilometers in careful, deliberate lines. And as scientists studied these streaks more closely, they realized what they were looking at. Geysers. Active eruptions, bursting up from beneath Triton's frozen crust, launching material several kilometers into its thin, delicate atmosphere before drifting back down, carried gently by faint winds, leaving behind those long, dark streaks across the pale ice. It was an extraordinary find, eerily reminiscent, in some ways, of the volcanic plumes discovered on Io, all those years earlier, back at the very beginning of the mission's journey through the solar system. But here, the mechanism was entirely different. Unlike Io's fiery, sulfur-driven volcanism, Triton's eruptions appeared to be driven by something far colder, likely nitrogen, transformed from solid to gas beneath the surface by faint warmth from the distant sun, building pressure until it finally burst upward through weaknesses in the icy crust, carrying dark, dusty material along with it. Think about that for a moment. A moon so far from the sun that sunlight itself arrives only as a faint, distant glow, and yet, even there, something was still active. Still moving. Still, in its own quiet, cold way, alive. It remains one of the most striking discoveries of Voyager 2's entire journey. Triton, this small, icy moon orbiting one of the coldest, most distant planets in the solar system, turned out to be geologically active, one of only a small handful of worlds, even today, known to display this kind of ongoing surface activity. It was a discovery that, much like Europa's cracked ice or Io's fiery plumes, quietly reshaped how scientists understood the outer solar system. These worlds were not simply frozen, unchanging relics, locked forever in stillness. Some of them, even now, continue to shift, erupt, and transform, slowly, patiently, largely unseen, far from the warmth and light of the inner solar system. As Voyager 2 completed its close study of Neptune and Triton, it marked the end of an extraordinary chapter, the final planetary encounter of the entire Voyager mission. 12 years after launching from Cape Canaveral, having traveled further than any spacecraft before it, Voyager 2 had now visited all 4 of the solar system's giant planets. Jupiter, Saturn, Uranus, and Neptune, uncovering volcanoes, lightning, hidden oceans, delicate rings, newly discovered moons, powerful storms, and now, finally, cold, quiet geysers erupting gently from the icy surface of a distant, long-overlooked moon. It is worth sitting, for a moment, with the scale of what had been accomplished. A single spacecraft, launched in the late summer of 1977, carrying instruments that, by today's standards, would seem almost impossibly simple, had traveled across billions of kilometers, over more than a decade, and had personally, directly, studied every single giant planet in our solar system. No other spacecraft, before or since, has managed to achieve quite the same thing. Voyager 2 remains, even now, utterly unique in that regard, a quiet, patient traveler, still drifting outward, long after its planetary work was complete. With Neptune and Triton now studied in detail, both Voyager spacecraft had, in their own separate ways, completed their primary missions. Voyager 1, having gathered its final planetary data at Saturn years earlier, was already climbing steadily upward, away from the plane of the planets, heading toward the very edge of the solar system itself. Voyager 2, having just finished its remarkable encounter with Neptune and Triton, now turned its attention outward as well, leaving the familiar structure of planets and rings behind, beginning the long, quiet journey toward interstellar space. 2 spacecraft. 2 long, separate paths. Both now facing the same vast, dark unknown that lay beyond everything they had already explored. But that, the journey beyond the planets, into the space between stars, would become an entirely new chapter of the story. One that, even now, continues quietly unfolding, decades later, as these small, aging spacecraft drift ever further from the only home they ever knew. For now, though, let Triton's faint geysers settle quietly back onto the ice. let Neptune's deep blue clouds drift slowly across that distant, storm-streaked atmosphere. And let Voyager 2 continue on, steady and unhurried, its long planetary journey finally complete, carrying with it, still, 2 golden records, and a quiet collection of discoveries that forever changed how we understand our small, remarkable corner of the universe. Let's return, once more, to Triton, because those strange, cold eruptions deserve a closer, more careful look. As Voyager 2's cameras studied the dark streaks scattered across Triton's icy surface, scientists began piecing together exactly what they were witnessing. These were not simply passive marks left behind by some ancient, long-finished process. They were active eruptions, caught quite literally in the act, geysers of nitrogen gas, mixed with fine, dark dust particles, bursting upward from beneath Triton's frozen crust and rising several kilometers into its thin, delicate atmosphere. From there, gentle high-altitude winds carried the dark material sideways, before it slowly drifted back down, settling onto the ice in long, faint trails that stretched for kilometers across the surface. It's a strange thing to picture, a moon so distant, so achingly cold, that its very surface is largely made of frozen nitrogen, and yet, somewhere beneath that frozen shell, enough warmth still lingers to occasionally push material upward, breaking through weaknesses in the ice, releasing quiet, cold eruptions into the near vacuum above. Nothing about Triton suggested it should be active. Its distance from the Sun placed it among the coldest environments Voyager had ever studied. And yet, here it was, quietly proving that stillness, even in such extreme cold, is never quite absolute. As scientists continued studying Triton, another puzzle slowly came into focus, one that had nothing to do with geysers or ice, but with the very shape of Triton's orbit around Neptune. Most large moons in our solar system orbit their parent planets in the same direction that the planet itself rotates, a natural, expected pattern, one that generally reflects how moons form alongside their planets, out of the same swirling disk of material in the early solar system. Triton, however, did something unusual. It orbited Neptune in the opposite direction, a retrograde orbit, moving against the planet's own rotation, rather than with it. This small but significant detail turned out to be an important clue. An orbit like this is very difficult to explain if a moon formed naturally alongside its planet. It strongly suggests something else entirely, that Triton did not originate as one of Neptune's original moons at all, but instead came from somewhere else, only to be captured later by Neptune's gravity, pulled into orbit rather than born there. Many scientists now believe that Triton once existed as an independent object, drifting through the outer solar system, perhaps similar in nature to the small, icy worlds found much further out, in the distant region known as the Kuiper Belt. At some point in the ancient past, Triton's path likely carried it close enough to Neptune that the planet's powerful gravity took hold, gradually pulling this wandering, icy world into a stable, though unusual, orbit, one that still, to this day, carries the telltale signature of its unlikely origin. There is something quietly poetic about that idea, a moon that was never truly meant to belong to Neptune at all, drawn in from the depths of the outer solar system, captured almost by chance, and held ever since in a slow, reluctant orbit around a planet it was never originally part of. Even now, billions of years later, that ancient, retrograde path remains as a quiet reminder of Triton's unusual, wandering history. With Triton's strange geysers documented, and its curious orbital history slowly coming into focus, Voyager 2 had, in many ways, completed its work among the planets. Both spacecraft, having now visited every giant world Voyager was ever designed to encounter, began settling into a very different phase of their long journey. What's remarkable, though, is that this was never supposed to last nearly as long as it has. When Voyager 1 and Voyager 2 were originally designed, engineers built them with a specific, limited mission in mind. The spacecraft were expected to operate for only a few years, enough time to reach Jupiter and Saturn, gather their data, and complete their primary scientific objectives. No one, not even the engineers who built them, fully expected these two small machines to still be functioning decades later, drifting quietly through regions of space no spacecraft had ever reached before. And yet, that is exactly what happened. Long after their original mission objectives were completed, long after Jupiter, Saturn, Uranus, and Neptune had all been left behind, Voyager 1 and Voyager 2 continued operating. Their instruments kept measuring. Their transmitters kept sending faint, patient signals back across the ever-increasing distance to Earth. What was originally planned as a mission lasting only a handful of years slowly transformed into something else entirely, one of the longest-running, most scientifically productive space missions in human history. Think about that, for a moment. Two spacecraft, built using the technology available in the mid-1970s, technology that, by today's standards, seems almost impossibly modest, have continued functioning for decades, far beyond anything their original designers dared to expect. Instruments meant to operate briefly have instead operated continuously, patiently, for well over 40 years, sending back data from regions of space that remain, even now, almost entirely unexplored by any other spacecraft. It's a quiet kind of resilience, the sort that doesn't announce itself loudly, but simply continues, year after year, decade after decade, doing exactly what it was built to do, long after anyone expected it to still be doing it at all. By 2012, that quiet persistence had earned Voyager an extraordinary distinction. In that year, the Voyager spacecraft became the longest operating spacecraft in the history of space exploration, surpassing every other mission ever launched, in terms of sheer, continuous operational time. No other spacecraft, before or since, had managed to keep functioning, keep gathering data, keep communicating with Earth, for quite as long as Voyager 1 and Voyager 2 already had by that point. And still, even now, decades later, they continue. But operational longevity was not the only remarkable distinction these two spacecraft would come to hold. There was also the simple, almost dizzying matter of distance. Years earlier, in February of 1998, Voyager 1 reached a quiet but significant milestone. On February 17th of that year, it passed the distance of another early spacecraft, Pioneer 10, which had been launched years before Voyager and had, until that moment, held the record as the most distant human-made object ever sent into space. As Voyager 1 continued its steady climb outward, it finally overtook that long-standing distance, becoming, at that moment, the single most distant object ever built by human hands. It's worth pausing on that thought for a moment, truly pausing and letting it settle. Somewhere out there, farther from Earth than any spacecraft before it, farther than Pioneer 10, farther than anything else humanity had ever launched into the dark, a small, aging machine, built in the 1970s, continued drifting quietly outward, carrying with it 2 golden records, a handful of quietly recorded greetings, and the accumulated data of an entire solar system's worth of discoveries. Voyager 1 did not slow down after reaching this milestone. It continued on, exactly as it had before, moving steadily outward, farther and farther from the only home it had ever known, setting a new distance record that, even today, it continues to hold and extend with every passing year. There is something almost impossible to fully grasp about that kind of distance, the sheer scale of it. Even now, as you listen to these words, Voyager 1 continues moving outward, carrying its quiet cargo of data and memory into regions of space that remain almost entirely unknown to us, farther from Earth than any human voice, any human signal, any human object has ever traveled before. 2 spacecraft, born from the same rare planetary alignment, launched only weeks apart in the late summer of 1977, have gone on to accomplish something far beyond what anyone, at the time, truly expected. Not simply a tour of the outer planets, remarkable as that alone would have been, but something larger. A quiet, patient endurance, stretching across decades, carrying humanity's curiosity, and its careful, hopeful greetings, further into the dark than anyone before them ever imagined possible. And still, even now, they continue outward. But what lies beyond the planets, beyond even the outer edges of what we typically consider our solar system, is a story still unfolding. A story of golden records drifting silently through interstellar space, of fading power, of quiet, careful decisions made by engineers back on Earth to keep these spacecraft alive for as long as possible. That story is still waiting, just ahead. For now, though, let Triton's faint geysers settle once more into stillness. Let the quiet record of Voyager 1's remarkable distance rest gently in the mind, vast and difficult to fully picture. And let both spacecraft continue on, steady and unhurried, carrying humanity's oldest, most patient message, quietly, faithfully, outward into the dark. As Voyager 1 continued its long, steady climb outward, farther from the sun than any spacecraft before it, it was, in a very real sense, entering entirely uncharted territory. Not simply in terms of distance, though that alone was extraordinary. It was approaching a boundary that no human-made object had ever crossed before, an invisible, shifting edge where the very nature of space itself begins to change. To understand what this boundary is, it helps to picture our sun not simply as a distant source of light and warmth, but as something more active, constantly releasing a steady stream of charged particles outward in every direction, known as the solar wind. This wind travels outward from the sun at extraordinary speeds, pushing against the thin, quiet material that fills the space between stars. For billions of kilometers, the solar wind remains dominant, carving out an enormous, invisible bubble around our entire solar system, a region known as the heliosphere. But the solar wind does not travel forever. As it moves further and further from the sun, its strength gradually fades. And at a certain distance, it begins to slow dramatically, pushed back by the faint, quiet pressure of interstellar space itself. This is the termination shock, the point where the solar wind, once moving faster than sound, abruptly slows, marking one of the first real boundaries between our solar system and the vast, open space that lies beyond it. In December of 2004, Voyager 1 reached this boundary. At a distance of roughly 94 astronomical units from the Sun, each astronomical unit representing the distance between Earth and the Sun itself. Voyager 1 crossed the termination shock, becoming the first spacecraft to directly measure this strange, distant transition. 94 times farther from the Sun than we are, drifting quietly through a region no spacecraft had ever reached before, Voyager 1 recorded the slowing of the solar wind, the first real sign that it was approaching the very outer edges of our Sun's influence. Nearly 3 years later, Voyager 2 reached the same boundary. In August of 2007, at a slightly closer distance of about 84 astronomical units, it too crossed the termination shock, confirming much of what Voyager 1 had already discovered, while adding its own detailed measurements from a slightly different point along that same great, invisible boundary. It's worth noting, quietly, just how strange and remarkable this achievement truly is. These two spacecraft, having already spent decades studying planets and moons, were now measuring something entirely different, not solid ground, not visible rings or storms, but the subtle, invisible behavior of particles and pressure, thinning and shifting at the very edge of our solar system's protective bubble. It was physics happening on a scale almost too vast to properly imagine, and yet, Voyager's instruments, faithfully, patiently, continued recording it all. But crossing the termination shock was not the end of this outward journey. Beyond it lay another region, quieter and more turbulent all at once, a slow, gradual transition zone where the solar wind, having already slowed dramatically, continues to fade further, gradually mixing with the faint material of interstellar space. This region would take Voyager 1 several more years to fully cross. Finally, in August of 2012, something extraordinary happened. On August 25, 2012, nearly 35 years after its launch from Cape Canaveral, Voyager 1 crossed the final boundary of the heliosphere entirely, leaving behind the last faint traces of our Sun's influence, and entering, for the first time in human history, true interstellar space. It became the first spacecraft ever to do so, the first human-made object to leave the protective bubble surrounding our entire solar system, and drift into the vast, open space that exists between stars. It is difficult to fully comprehend the significance of that moment. For the first time ever, a piece of human engineering, carrying with it two golden records, quiet greetings, images of Earth, recordings of human voices and laughter and music, had crossed beyond the only environment our Sun has ever shaped, moving now through space filled not with solar wind, but with the faint, ancient material that drifts slowly between the stars themselves. Space that had, until that very moment, never once been directly touched, or measured, or experienced by anything built by human hands. Voyager 1 did not stop, of course. It continued exactly as it always had, steady and unhurried, its instruments quietly recording the strange, subtle differences of this new environment, a colder, quieter kind of space, filled with different particles, different magnetic patterns, different faint signatures of a much older, much larger galaxy stretching out endlessly in every direction. 6 years later, Voyager 2 followed. On November 5, 2018, Voyager 2 also crossed the boundary of the heliosphere, becoming the second spacecraft ever to enter interstellar space. Though it followed a different trajectory than its twin, having traveled past Uranus and Neptune along its own separate path, it eventually reached this same profound threshold, leaving behind the protective influence of our Sun, and joining Voyager 1 in the vast, quiet region that exists between stars. It's worth reflecting, for a moment, on what this really means. Voyager 1 reached interstellar space in 2012. Voyager 2 followed in 2018. Two spacecraft, launched only weeks apart back in 1977, now separated not only by distance and direction, but by 6 years in terms of when each one finally crossed this extraordinary threshold. And yet, in a much larger sense, they remain connected, two halves of the very same remarkable achievement, each having accomplished something no other spacecraft, before or since, has ever managed to do. To this day, Voyager 1 and Voyager 2 remain the only two spacecraft ever to operate beyond the heliosphere, the only human-made objects that have ever truly passed into interstellar space. Every other mission, every other satellite, every other spacecraft ever launched by any nation on Earth, has remained within the boundaries of our Sun's influence, circling planets, studying moons, drifting through the inner and outer reaches of our solar system, but never once crossing that final, quiet threshold into the space that lies beyond it. It is a distinction unlikely to be matched again anytime soon. Very few spacecraft are ever built with the kind of endurance, the kind of longevity, required to survive a journey this long, decades of continuous operation, traveling billions of kilometers, simply to reach the edge of where our Sun's influence finally fades away. Voyager 1 and Voyager 2, remarkably, were built exactly that way, not necessarily by original design, but through a combination of careful engineering, redundant systems, and, perhaps, a quiet kind of fortune, allowing them to continue functioning decades beyond their original, modest mission plans. Even now, both spacecraft continue drifting outward, farther still, into this vast, largely unexplored region of space. Their instruments, aging but still functional, continue measuring the faint particles, the subtle magnetic fields, the quiet, ancient material that fills the space between stars, data that scientists back on Earth continue to study carefully, learning, for the very first time, what conditions are actually like beyond the protective boundary that has shaped our entire solar system since its formation. There is something deeply moving about this ongoing journey. Two small, aging spacecraft, launched decades ago, using technology that seems almost impossibly modest by today's standards, continuing to drift patiently outward, carrying with them humanity's careful, hopeful greetings, quietly gathering knowledge from a region of space no one before them had ever directly experienced. They are, in the truest sense, travelers now, no longer studying planets or moons, no longer capturing images of rings or storms or distant, icy landscapes. Instead, they drift quietly through the vast, dark ocean of interstellar space itself, carrying forward the same quiet purpose they were given decades earlier: to explore, to measure, to observe, and, if the moment should ever somehow arise, to greet whatever, or whoever, might one day be listening. Ahead of them now lies nothing but open space, distances so vast that even the concept of measuring them in familiar terms begins to lose meaning. And yet, they continue. For now, let that quiet threshold remain, fixed gently in the mind, the exact moment each spacecraft slipped silently beyond the reach of our sun, entering a realm of space entirely new to human experience. Let Voyager 1 and Voyager 2 continue their slow, patient drift outward, two small, steady travelers, carrying Earth's quiet hello ever deeper into the vast, dark silence that lies between the stars. Once Voyager 1 had crossed into interstellar space, its work was, in many ways, only just beginning. It was no longer simply a spacecraft that had reached a historic boundary. It had become something closer to an instrument of discovery for an entirely new kind of science, one focused not on planets or moons, but on the very fabric of space itself, far beyond anything our sun directly touches. Among its many achievements in this new environment, Voyager 1 became the first spacecraft ever to directly measure the magnetic field present in interstellar space. For decades, scientists had theorized about what this magnetic field might look like, how strong it might be, how it might be oriented relative to our own solar system. But theories, however carefully reasoned, are not the same as direct measurement. As Voyager 1 drifted quietly through this new region, its instruments finally captured real, concrete data, revealing the actual structure and strength of the magnetic field that quietly permeates the space between stars. It also became the first spacecraft to measure something else entirely, the density of the interstellar medium itself, the thin, faint material, mostly gas and dust, that fills the vast spaces between stars. For most of human history, this material had existed only as a theoretical concept, inferred indirectly through careful observation of starlight and distant astronomical phenomena. But Voyager 1, simply by being there, simply by drifting slowly through this quiet, nearly invisible material, was able to measure it directly for the very first time, turning abstract calculations into real, confirmed data. Meanwhile, Voyager 2 had already made its own quiet contribution to this growing body of knowledge. Years earlier, as it crossed the termination shock in 2007, it became the very first spacecraft to directly measure that particular boundary, the point where the solar wind abruptly slows as it pushes against the pressure of interstellar space. While Voyager 1 had crossed this same boundary 3 years earlier, its instruments for measuring solar wind conditions were, by that time, no longer fully functioning. Voyager 2, still carrying working instruments for this particular kind of measurement, was able to capture data that Voyager 1 simply could not, offering scientists a rare, detailed look at exactly how the solar wind behaves as it finally slows and fades at this distant, invisible edge. Together, these two spacecraft, each contributing measurements the other could not, gave scientists an extraordinarily complete picture of this remote boundary, a picture that could only have been assembled by having two separate spacecraft, traveling along two separate paths, each carrying slightly different instruments, each reaching these regions at slightly different times. But perhaps one of the most striking discoveries to emerge from Voyager 1's time in interstellar space involved something far smaller, far more subtle than magnetic fields or particle density: cosmic rays. Cosmic rays are tiny, incredibly fast-moving particles, remnants of powerful cosmic events like distant supernovae, traveling through the galaxy at extraordinary speeds. Near our Sun, many of these particles are deflected or slowed by the solar wind, which acts as a kind of protective shield, gently pushing back against much of this high-energy radiation before it ever reaches the inner solar system. It was one of the quiet, often overlooked benefits of living within the heliosphere, a natural kind of shelter, shaped entirely by our own sun. As Voyager 1 moved beyond this protective boundary, its instruments recorded something remarkable. Cosmic rays, once outside the heliosphere, were found to be roughly 4 times more abundant than they are closer to the Sun. It was a striking confirmation of just how significant our Sun's protective influence truly is, and a quiet, sobering reminder of just how different, how much harsher, conditions become once that protection is left behind. It's worth pausing, for a moment, to consider what that really means. For our entire existence, life on Earth has developed and evolved within this relatively sheltered bubble, gently shielded from much of the wider galaxy's more intense radiation. Only now, through Voyager's instruments, drifting quietly far beyond that shelter, do we have real, direct evidence of just how different, just how much more exposed, conditions become once you leave that protection behind. As both spacecraft continued their outward journeys, another quiet detail became increasingly apparent: the two were no longer following anything resembling a shared path. Voyager 1, having earlier been deliberately angled upward, away from the plane in which the planets orbit the Sun, in order to capture that detailed encounter with Titan, continued along this same upward trajectory, drifting steadily above the solar system's main orbital plane. This particular path, as it turned out, happened to carry it toward the boundary of the heliosphere more directly, allowing it to reach interstellar space several years before its twin. Voyager 2, meanwhile, continued along its own separate route, traveling steadily beneath that same orbital plane, following the path that had earlier allowed it to visit Uranus and Neptune. This lower trajectory, while equally valid, equally significant, simply required slightly more time and distance before finally reaching the edge of the heliosphere in 2018. It's a quiet, almost poetic detail when you think about it. 2 spacecraft, born from the very same rare planetary alignment, launched only weeks apart from the very same launch site, are now drifting outward in genuinely different directions, one climbing above the solar system's disk, the other continuing steadily beneath it. Neither path was better or worse than the other. Each was simply shaped by the specific discoveries each spacecraft was designed to make. Titan's atmosphere on one path, Uranus and Neptune on the other. And so, even now, decades later, Voyager 1 and Voyager 2 continue moving apart, each following its own long, solitary arc, carrying its own separate set of discoveries, its own separate golden record, into 2 very different regions of the vast space that lies beyond our solar system. Even today, both spacecraft remain active, still transmitting faint, patient signals back toward Earth, still drifting steadily outward, farther and farther with each passing year. Voyager 1 continues moving away from the Sun at a speed of roughly 3.6 astronomical units per year, a pace that, while extraordinary by human standards, remains almost imperceptibly slow when measured against the truly vast distances of interstellar space. Voyager 2, meanwhile, continues its own outward journey at a slightly slower pace, moving away from the Sun at approximately 3.3 astronomical units each year. It's difficult, perhaps, to fully picture speeds like these in any meaningful way. 3.6 astronomical units, remember, means 3.6 times the distance between Earth and the Sun, covered by Voyager 1 in a single year. And yet, even at this remarkable pace, the true scale of interstellar space remains almost incomprehensibly vast. At this rate, it will still take both spacecraft many thousands of years simply to approach the outer edges of what's known as the Oort cloud, a distant, sparse region of icy debris that marks the true, outermost boundary of our Sun's gravitational influence. They are not simply fast. They are patient, incredibly, almost impossibly patient, continuing their slow, steady drift outward, year after year, decade after decade, carrying forward the same quiet purpose they were given back in 1977. There is something deeply calming, in a way, about that kind of patience. In a universe defined by almost unimaginable distances and timescales, Voyager 1 and Voyager 2 continue their journey not with urgency, but with quiet persistence, small, aging machines, moving steadily outward through the dark, carrying with them humanity's careful measurements, its quiet curiosity, and its hopeful, golden greetings, continuing on, exactly as they always have, into the endless, patient dark that lies ahead. For now, let that steady, gentle motion settle quietly in the mind. 3.6 astronomical units each year. 3.3 astronomical units each year. Small numbers, perhaps, against the vastness of interstellar space, and yet, faithfully, patiently, carrying two small spacecraft ever deeper into the silent, star-filled dark that lies beyond everything we have ever truly known. Both spacecraft, even now, continue that same slow, steady escape from the solar system, each one moving outward at more than 3 astronomical units every year, a pace that, while gentle by cosmic standards, has nonetheless carried them further from home than any other human-made object in history. Voyager 1, slightly faster, continues at roughly 3.6 astronomical units annually. Voyager 2, just behind, moves at approximately 3.3. Small differences, perhaps, when written down as numbers, but across the coming centuries, these tiny variations in speed will continue to separate the two spacecraft further and further, each one drawing its own long, solitary line through the emptiness of interstellar space. What remains truly remarkable, though, is not simply that these spacecraft continue moving. It's that they continue functioning at all. Voyager 2, even now, continues to return genuinely useful scientific data, a fact that would have seemed almost unbelievable to the engineers who built it, back in the mid-1970s. Its instruments, and the radioisotope power source that quietly fuels them, have lasted far longer than anyone originally anticipated. This power source works by harnessing the slow, natural decay of radioactive material, converting that steady release of heat into usable electricity, a method chosen specifically because it does not rely on sunlight, which becomes increasingly faint and unreliable the farther a spacecraft travels from the Sun. It was a wise decision, made decades ago, and one that has allowed both spacecraft to continue operating in regions of space so distant, so dim, that solar power would have failed them long ago. Even so, this radioactive power source does not last forever. It decays slowly, gradually producing less and less electricity with each passing year, a quiet, inevitable countdown that mission engineers have had to manage carefully, thoughtfully, for decades. Voyager 1, remarkably, still has 2 scientific instruments actively operating, even now, nearly 49 years after its original launch. Think about that, for a moment. A spacecraft built using the technology of the 1970s, launched before most of today's engineers were even born, continues, even now, to gather and transmit real scientific data from a region of space more distant, more remote, than anywhere else humanity has ever directly explored. Maintaining that kind of longevity, though, has required difficult, deliberate choices. As Voyager 1's power supply has slowly, steadily diminished over the decades, NASA has had to make careful decisions about which instruments to keep running, and which ones, reluctantly, needed to be turned off. One by one, over the years, certain instruments have been shut down, not because they stopped working, but simply because there was no longer enough power to keep every system running at once. It's a quiet, careful balancing act, extending the spacecraft's life for as long as possible, by focusing its remaining power only on the instruments considered most valuable, most essential to the mission's ongoing scientific goals. It's a strange kind of preservation, in a way, managing a spacecraft's slow decline not by trying to stop it entirely, but by accepting it gradually, thoughtfully, making careful choices at each stage that allow the mission to continue just a little longer, and then a little longer still. And what makes this ongoing effort so remarkable is that both spacecraft continue to serve a genuine scientific purpose, one quite different from what they were originally built for. Voyager 1 and Voyager 2 are no longer simply remembered for their extraordinary tour of the outer planets, remarkable as that achievement remains. Today, they continue their work as active tools for studying the edge of interstellar space itself, a region that, without these 2 aging spacecraft, would remain almost entirely unexplored, known only through distant, indirect observation rather than direct, first-hand measurement. It's a quiet kind of second purpose, discovered almost by accident, simply because these spacecraft happen to survive far longer than anyone originally expected. What began as a mission to study Jupiter and Saturn slowly transformed into something else entirely, a decades-long study of the very boundary between our solar system and the wider galaxy beyond it. But amid all of these remarkable scientific achievements, the discoveries, the record-breaking distances, the decades of careful data collection, there remains one image, captured by Voyager 1, that stands apart from everything else. Not for its scientific value, though it holds some, but for what it represents, quietly, powerfully, to anyone who has ever looked at it. In February of 1990, as Voyager 1 was completing its final imaging tasks before its cameras were permanently powered down to conserve energy, mission scientists made an unusual request. Rather than pointing its camera outward, toward the endless dark ahead, they asked Voyager 1 to turn around, to look back, one final time, toward the tiny, distant world it had left behind so many years earlier. From a distance of about 3.7 billion miles, Voyager 1 captured an image of Earth, not as a vast, detailed world, filled with oceans and mountains and cities, but as something almost impossibly small. A single, faint point of light, barely more than a pixel, suspended in a thin beam of sunlight scattered across the camera's lens. Carl Sagan, the very same scientist who had helped select the contents of the Golden Records years earlier, later gave this image a name that has endured ever since: the pale blue dot. It's difficult to fully describe the quiet power of that photograph. Everyone who has ever lived, every person we have ever known, ever loved, ever admired or mourned or simply passed by on a crowded street, existed entirely within that single, faint speck of light, suspended against the overwhelming darkness of space. Every war ever fought, every home ever built, every quiet, ordinary moment of human life, took place there, on that tiny, fragile point, drifting silently through the vastness of the cosmos. From 3.7 billion miles away, Earth does not look significant. It does not look powerful, or important, or central to anything at all. It simply looks small, fragile, alone. And yet, everything we have ever known exists there. It remains one of the most quietly profound images ever captured, not because of what it shows in detail, since there is barely any detail to see at all, but because of what it represents. A gentle, humbling reminder of just how small our entire world truly is, when viewed from far enough away, and, perhaps, a quiet invitation to appreciate, just a little more carefully, the small, fragile place we all call home. As Voyager 1 continues its long journey outward, farther still from that pale, distant dot of light, it carries with it not only its remaining scientific instruments, and its 2 golden records, but also this quiet, lasting image, a photograph that will likely remain, for as long as human civilization endures, one of the most meaningful pictures ever taken. And still, the journey continues. Scientists estimate that it will be roughly 40,000 years before Voyager 1 comes anywhere near another star, a length of time so vast, so far beyond ordinary human experience, that it becomes almost impossible to truly comprehend. 40,000 years from now, long after everything familiar to us today has changed beyond recognition, Voyager 1 will still be drifting quietly through interstellar space, carrying forward the same quiet message it has carried since 1977. Slow, patient, and utterly alone in the vast, dark distances between the stars. For now, though, let that pale blue dot rest quietly in the mind, small and fragile, suspended gently within a single beam of scattered light. Let Voyager 1 and Voyager 2 continue their long, unhurried journey outward, their instruments quietly humming in the cold and the dark, still listening, still measuring, still faithfully carrying humanity's quiet curiosity ever further into the silent unknown that lies ahead.